Imagine you're standing in a room and someone hands you a ball. You hold it in your hand, you feel its weight, you know exactly where it is, and if someone asked you how fast it was moving, you'd say it's not. It's just sitting right here in my palm. Simple. You know where the ball is and what it's doing. That's how the world works, right? That's how everything works. You throw the ball, and if you knew exactly how hard you threw it and at what angle, and you could account for the wind and the spin, you could, in theory, predict exactly where it would land. Every time. The universe, at least the one you and I walk around in every day, feels like a giant machine. Push something here, it moves over there. Cause and effect. Predictable. Sensible. Now here's the thing. There is a layer underneath all of that, a deeper level of reality where none of those rules apply, where a particle can be in two places at once, where the act of looking at something changes what it does, where certainty itself, the basic idea that you can know where something is and where it's going, turns out to be fundamentally, mathematically, provably impossible. This is quantum mechanics, and it is, by almost universal agreement among physicists and students and philosophers, and honestly anyone who has ever sat with it long enough, the most confusing concept in all of physics, maybe in all of science. And tonight, slowly, gently, with no rush at all, we're going to walk through it together. Not the equations, not the formalism, the story. The human story of how we got here, who figured it out, what they were trying to solve, and why the answers they found were so strange that some of the smartest people who ever lived refused to accept them. And it starts, as so many things in physics do, with light. Let's go back to the late 1600s. Isaac Newton, a name you know, is in England, and he's doing something deceptively simple. He's playing with prisms. He takes a beam of sunlight, passes it through a triangular piece of glass, and watches it fan out into a rainbow. Red, orange, yellow, green, blue, violet. He concludes that white light is not pure. It's a mixture. It's made up of all those colors combined. And he goes further. He argues that light is made of tiny particles, little corpuscles he calls them, streaming out from a source like a lantern throwing off sparks. This makes intuitive sense. Light travels in straight lines. It bounces off mirrors. It casts sharp shadows. It behaves in many ways like a stream of tiny bullets. But not everyone agrees. Across the English Channel, a Dutch scientist named Christian Huygens has a completely different idea. Huygens says light is a wave, not particles at all, but a ripple, like the ripple you see when you drop a pebble into still water. He argues that this explains things Newton's particle theory can't quite handle, like the way light bends slightly around corners, or the way two beams of light can interfere with each other, creating patterns of brightness and darkness that look exactly like what happens when two sets of water waves overlap. Now here's the thing about Newton. He's Isaac Newton. By the early 1700s, he's arguably the most famous scientist in the world. He's invented calculus, he's described the laws of motion, he's explained gravity. When Newton says light is particles, people listen. And for about a century, the particle theory dominates. Huygens' wave idea gets shelved. Not disproven, just overshadowed. Think about what that means. For 100 years, the physics community largely goes with the wrong answer, or at least the incomplete one, partly because of the sheer weight of one man's reputation. That happens more in science than people like to admit. But then, in 1801, a young English polymath named Thomas Young, does something beautifully simple that changes everything. He sets up what's now called the double-slit experiment, and you should remember that name because we're going to come back to it several times tonight, and each time it's going to get stranger. Here's what Young does. He takes a beam of light and shines it at a barrier that has two very narrow slits cut into it, side by side. Behind the barrier, there's a screen. Now, if light were made of particles, little bullets flying through the air, you'd expect to see two bright bands on the screen, one behind each slit. Makes sense, right? Bullets go through one slit or the other. They hit the wall behind it. You get two stripes. Simple. But that's not what Young sees. Instead, he sees a pattern of alternating bright and dark bands spread across the screen, an interference pattern. And if you've ever watched two sets of ripples in a pond collide, you know exactly what this looks like. Where two wave crests meet, they reinforce each other. You get a bright band. Where a crest meets a trough, they cancel each other out. You get darkness. This is something only waves do. Particles don't cancel each other out. Particles don't interfere. Young's experiment is, for all practical purposes, proof that light is a wave. And over the course of the 1800s, the evidence piles up. In the 1860s, a Scottish physicist named James Clerk Maxwell, one of the true giants of the field, works out a set of 4 equations that describe electricity and magnetism as two aspects of a single force, electromagnetism. And when he does the math, he discovers something remarkable. His equations predict the existence of waves, electromagnetic waves, that travel at a specific speed. And that speed, when he calculates it, turns out to be almost exactly the measured speed of light. The implication is stunning. Light is an electromagnetic wave. It's the same kind of thing as radio waves, just at a much higher frequency. Maxwell's equations are elegant, powerful, and they tie together electricity, magnetism, and optics into one unified framework. By the late 1800s, physicists are feeling pretty confident. Light is a wave. The universe is mechanical. Newton's laws handle the big stuff. Maxwell's equations handle the electromagnetic stuff. And between the two of them, physics is, in the view of many, nearly complete. There's a famous, possibly apocryphal story that around this time, a prominent physicist, often said to be Lord Kelvin, declared that there was nothing new to be discovered in physics, that all that remained was more and more precise measurement. That turned out to be spectacularly wrong, because there were cracks, small ones, but real, problems that the existing physics couldn't solve. And the first one, the one that would eventually blow the whole thing open, had to do with something that sounds almost comically mundane. It had to do with the color of hot things. You know this from everyday experience, even if you've never thought about it in physics terms. Heat up a piece of metal and it starts to glow. First a dull red, then orange, then yellow, then, if you get it hot enough, white. The color changes with temperature. This is called black body radiation, and by the 1890s, physicists were trying to write down a formula that would predict exactly how much light at each color a hot object gives off. It should have been straightforward. You take Maxwell's equations, you apply the known laws of thermodynamics, you do the math, and you get your answer. But the answer was wrong. Not a little wrong. Catastrophically wrong. The formulas that classical physics produced predicted that as you move toward higher frequencies, toward the blue and ultraviolet end of the spectrum, the amount of energy radiated should increase without limit. it should go to infinity. A hot object, according to the math, should be blasting out infinite energy in ultraviolet light. This obviously doesn't happen. Your toaster does not kill you with a death ray of ultraviolet radiation every morning. Physicists called this the ultraviolet catastrophe, and it's a great name because it really was a catastrophe, not for the universe, which was doing fine, but for the theory that was supposed to describe it. And this is where a quiet, meticulous German physicist enters the story. His name is Max Planck, and in the year 1900, he does something radical, something that he himself is deeply uncomfortable with. He finds a mathematical trick that fixes the problem. But it's not just a trick. It's a fundamental break with everything physics has assumed for centuries. Here's what Planck does. Instead of treating energy as continuous, as something that can flow in any amount, like water from a tap, he proposes that energy comes in tiny, discrete packets, little chunks. He calls them quanta, from the Latin word for how much. And the size of each quantum depends on the frequency of the light. Higher frequency light, bluer light, comes in bigger packets. Lower frequency light, redder light, comes in smaller ones. The relationship is simple and beautiful. The energy of one quantum equals the frequency of the light multiplied by a constant, a tiny, tiny number that we now call Planck's constant. And when he plugs this assumption into the math, the ultraviolet catastrophe vanishes. The formula works. It matches the experimental data perfectly. The reason a hot object doesn't radiate infinite ultraviolet energy is that at high frequencies, each quantum of energy is so large that the object simply can't produce them in unlimited quantities. The energy comes in chunks, and the chunks get too expensive, in energy terms, for the object to keep paying. Now, think about what Planck has just done. He said that energy is not smooth, it's grainy. It comes in indivisible little pieces. This is a profoundly weird claim. It's like saying you can walk 1 step or 2 steps, but you can never take 1.5 steps. There's a minimum unit, and you can't go below it. In the everyday world, energy seems perfectly continuous. You can push a swing a little harder or a little softer, in any amount you like. But Planck is saying that at the deepest level, that's an illusion. There's a graininess to reality that only shows up when you look very, very closely. And here's the remarkable part. Planck himself doesn't really believe it. He sees it as a mathematical convenience, a trick that happens to give the right answer. He expects that someone, eventually, will find a way to derive the same result without this strange assumption about quanta. He spends years trying to undo his own discovery. He can't. Nobody can. Because it's not a trick, it's real. But in 1900, nobody fully grasps this yet. Planck has lit the fuse, but the explosion hasn't happened. The word quantum has entered physics, but its full implications are still hidden. It will take another mind, a younger mind, someone willing to push Planck's idea much further than Planck himself ever wanted to go, to show just how deep this rabbit hole really goes. That person is working in a patent office in Bern, Switzerland. He's 26 years old. He's been unable to get an academic position, and in his spare time, between evaluating patent applications for electromagnetic devices, he's thinking about light. His name is Albert Einstein, and in 1905, the same year he publishes his theory of special relativity, the same year he explains Brownian motion, he writes a paper about something called the photoelectric effect. And this paper, more than any other single document, is the one that takes Planck's reluctant idea and turns it into a revolution. The photoelectric effect is another one of those problems that classical physics can't explain. Here's the setup. You shine light on a metal surface, and sometimes the light knocks electrons loose from the metal. That's the photoelectric effect. Simple enough. But the details are baffling. If light is a wave, then brighter light should knock electrons out with more energy, the way bigger ocean waves hit harder. But that's not what happens. Brighter light knocks out more electrons, but each individual electron comes out with the same energy regardless of brightness. What changes the energy of each electron is the color of the light. Bluer light, higher frequency, kicks electrons out harder. Redder light, lower frequency, barely kicks them out at all, and below a certain frequency, no electrons come out, no matter how bright you make the light. Classical wave theory cannot explain this. It makes no sense if light is a smooth, continuous wave. But Einstein sees it. He takes Planck's idea and pushes it one enormous step further. He says that light itself is quantized. Not just the energy of the atoms emitting it, but the light itself. Light comes in particles, discrete packets of energy, each one carrying exactly the amount of energy that Planck's formula predicts. Einstein calls them light quanta. We now call them photons. And suddenly, the photoelectric effect makes perfect sense. Each photon hits one electron. If the photon carries enough energy, determined by its frequency, the electron gets knocked free. If it doesn't, nothing happens, no matter how many low-energy photons you throw at the surface. Brightness just means more photons, not more energetic ones. It's like the difference between being hit by 100 ping-pong balls versus one baseball. The ping-pong balls, no matter how many, might never break a window. The baseball breaks it on the first throw. So now we have a problem. A beautiful, maddening, world-altering problem. Thomas Young's double-slit experiment from a century earlier proved that light is a wave. Einstein's explanation of the photoelectric effect proves that light is a particle. Both experiments are correct. Both results are real. Light is somehow, impossibly, both. It behaves like a wave when you test it one way, and like a particle when you test it another way. And this isn't a failure of our instruments or our cleverness. It's not that we just haven't figured out the right description yet. It seems to be a fundamental feature of reality itself. This is where the strangeness begins in earnest. And in the years following 1905, as physicists start to grapple with what Planck and Einstein have uncovered, they're going to discover that this wave-particle duality isn't just a quirk of light. It applies to matter too, to electrons, to atoms, to everything. The solidity of the world, the certainty of it, the way things seem to have definite positions and definite speeds, all of that is about to dissolve into something far more elusive and far more beautiful. And the person who takes the next step, who shows that even the atom itself is nothing like what anyone imagined, is a young Danish physicist named Niels Bohr, working in a laboratory in Manchester, England, staring at the strange, unexplained patterns in the light emitted by hydrogen gas, and wondering why those colors, and only those colors, kept showing up every single time. See, here's what was puzzling Bohr. When you heat up hydrogen gas, or run an electric current through it, it glows. But it doesn't glow white, the way a hot piece of metal does. It glows in very specific colors. If you take that light and pass it through a prism, spreading it out the way Newton did centuries earlier, you don't get a smooth rainbow. You get a handful of sharp, bright lines, each one a precise color, sitting against a dark background. Red, blue-green, violet, deep violet. Always the same lines, always the same positions, always the same gaps between them. By the time Bohr arrived in Manchester in 1912, these spectral lines had been measured with extraordinary precision. A Swiss schoolteacher named Johann Balmer had even found a mathematical formula, back in 1885 that predicted the wavelengths of the visible hydrogen lines perfectly. But Balmer's formula was just a pattern. It was like noticing that the addresses on one side of a street are all odd numbers. You can predict the next address, sure, but that doesn't tell you why the city planners laid it out that way. Nobody could explain why hydrogen emitted those specific wavelengths and no others. Classical physics had no mechanism for it. According to classical electromagnetism, an electron orbiting a nucleus should radiate energy continuously, spiraling inward as it loses energy, sweeping through every possible frequency on the way down, and then crashing into the nucleus in a fraction of a second. Every atom should collapse almost instantly. Obviously, atoms don't collapse. You're made of atoms, and you're still here. So something was deeply, fundamentally wrong with the classical picture. And Bohr, who was 26 years old at the time and had this remarkable combination of physical intuition and philosophical stubbornness, looked at that problem and did something radical. He borrowed Planck's idea. He said, "What if the electron can't just orbit at any distance it likes? What if, just like Planck's oscillators could only vibrate at certain energies, the electron in an atom can only exist at certain specific energy levels? Certain allowed orbits and nothing in between. Think about what that means. Imagine you're climbing a staircase. You can stand on the first step, or the second step, or the third. But you can never stand at 1.5 steps. Your foot is either on a step, or it isn't." Bohr was saying that electrons work the same way. They can occupy the first energy level, or the second, or the fifth, but they can never exist in between. And when an electron jumps from a higher step to a lower one, it releases energy. Not a random amount of energy, but a very precise amount, exactly equal to the difference between those two levels. That energy comes out as a photon, a particle of light, with a wavelength that corresponds to that exact energy gap. And that's why hydrogen only glows in certain colors. Each color is a specific jump between specific energy levels. The red line is one jump. The blue-green line is a different jump. The violet lines are still other jumps. The spectrum isn't random. It's a map of the atom's internal staircase. Bohr published this model in 1913, and it was immediately, spectacularly successful at predicting the hydrogen spectrum. Balmer's formula, that mysterious pattern from 1885, fell right out of Bohr's theory. The numbers matched, not approximately, not roughly. They matched to several decimal places. That kind of agreement between theory and experiment is the sort of thing that makes physicists sit up very straight in their chairs. But here's the thing. Bohr's model was also, in a certain sense, completely unjustified. He couldn't explain why only certain orbits were allowed. He just declared it. He said, essentially, I'm going to assume this is true, and look, it works. There was no deeper mechanism, no underlying reason. It was a rule imposed from outside, and it felt arbitrary, even though it gave the right answers. Some physicists were thrilled, others were deeply uncomfortable. Einstein himself said something along the lines of, "This is one of the greatest discoveries," but he also recognized that it raised as many questions as it answered. And Bohr knew this. He wasn't naive about the limitations, but he had a philosophical temperament that was, in many ways, perfectly suited to what quantum physics was about to become. He was comfortable with ambiguity. He was comfortable saying, "We don't fully understand this yet, but the evidence tells us it's true. So let's keep going and see where it leads." That willingness to sit with discomfort, to accept a result even when it offended your intuition, would become one of the defining traits of the quantum revolution. And Bohr, more than almost anyone else, would become its philosophical champion. Now let's sit with that for a second. By 1913, we've got Planck saying energy comes in packets, Einstein saying light itself is made of particles, Bohr saying electrons in atoms can only exist at certain energy levels. Each of these ideas chips away at the smooth, continuous, predictable universe that classical physics had built. But they're still, at this point, a collection of separate insights, brilliant insights, revolutionary insights, but not yet a unified theory. They're patches on a cracking dam. And the dam is about to break wide open, because in the early 1920s, a handful of young physicists, most of them barely out of their 20s, are going to take these scattered clues and forge them into something entirely new. A complete mathematical framework for understanding the subatomic world. And the story of how that happens is one of the most extraordinary intellectual dramas of the 20th century. Let me introduce you to a few of these people, because they matter, not just as names in a textbook, but as personalities. The way quantum mechanics developed was shaped profoundly by the specific human beings who built it, their temperaments, their rivalries, their friendships, their arguments at dinner tables and on long walks. First, there's Werner Heisenberg, German, born in 1901, so he's barely 20 when he starts making contributions that will reshape physics. Heisenberg was brilliant in a way that was almost unsettling to the people around him. He could hold enormous mathematical structures in his head and manipulate them without writing anything down. He was also intensely competitive, ambitious, and sometimes prickly. He studied under Arnold Sommerfeld in Munich, and then under Max Born in Göttingen, and by his early 20s, he was already pushing at the boundaries of what Bohr's atomic model could do. Then there's Erwin Schrödinger, Austrian, older than Heisenberg by more than a decade, born in 1887. Schrödinger was cultured, literary, a lover of philosophy and poetry, and he had a very different temperament. Where Heisenberg was abstract and algebraic, Schrödinger was visual and intuitive. He wanted to be able to picture what was happening. He wanted a theory you could see, in some sense. He wanted waves. And then there's Louis de Broglie, French, a prince, actually, from an old aristocratic family. De Broglie had started out studying history before switching to physics. And in 1924, in his doctoral thesis, he proposed something that sounds almost absurd when you first hear it. He said, if light, which everyone thought was a wave, turns out to also be a particle, then maybe matter, which everyone thinks is made of particles, is also a wave. That's it. That's the idea. And it's one of those moments in the history of science where you want to pause and appreciate the sheer audacity of it. De Broglie was a graduate student. He was proposing that electrons, those tiny, solid, definite little things that everyone had been thinking of as particles since J.J. Thomson discovered them in 1897, had a wavelength, that they could diffract and interfere, just like light does. He even provided a formula. The wavelength of any particle, he said, is equal to Planck's constant divided by the particle's momentum. The heavier and faster something is, the shorter its wavelength. For everyday objects, like a baseball or a person, the wavelength is so unimaginably tiny that it's completely undetectable. But for something as light as an electron, the wavelength is big enough to matter, big enough to show up in experiments. Now, de Broglie's thesis committee wasn't quite sure what to make of this. The idea was so strange that they sent a copy to Einstein for his opinion. And Einstein, to his credit, immediately recognized its importance. He called it a very notable publication and said that de Broglie had lifted a corner of the great veil. With Einstein's endorsement, the thesis was accepted, and de Broglie got his doctorate. He would later win the Nobel Prize for this work in 1929. But here's what's really clever about what de Broglie had done. Remember Bohr's model of the atom with its mysterious allowed orbits? Bohr had simply declared that only certain orbits were permitted without explaining why. De Broglie's matter waves gave a reason. If an electron is a wave, then it can only exist in orbits where it fits perfectly, where the circumference of the orbit is exactly a whole number of wavelengths. 1 wavelength, 2 wavelengths, 3 wavelengths. Like a vibrating guitar string that can only sustain certain notes, the ones where the wave pattern fits neatly between the fixed ends. Any other orbit, and the wave would interfere with itself destructively and cancel out. It wouldn't be stable. It couldn't persist. So the allowed orbits aren't arbitrary at all. They're the only ones where the electron's wave can sustain itself. That's beautiful. That's the kind of explanation that makes you lean back and just breathe for a second. A puzzle that had been nagging at physicists for over a decade, why only certain orbits, suddenly had an answer that felt natural and almost inevitable. The quantization of the atom wasn't a strange rule imposed from outside. It was a consequence of something deeper. Matter is wave-like, and waves have to fit. And this is where things start moving very fast. Because once you accept that particles are waves, you need a wave equation. You need mathematics that describes how these matter waves behave, how they move, how they interact, how they evolve over time. And two very different approaches to that mathematics are about to emerge, almost simultaneously, from two very different minds. Heisenberg is going to build one version, abstract, algebraic, built on matrices and observable quantities. Schrödinger is going to build another, visual, intuitive, built on a smooth wave equation that looks almost classical. They will seem, at first, like completely different theories. And the argument over which one is right, over what quantum mechanics actually means, is going to become one of the most heated and consequential debates in the history of science. It starts in the summer of 1925, on a small, windswept island in the North Sea called Helgoland, where a 23-year-old Werner Heisenberg, suffering from terrible hay fever and unable to sleep, begins scribbling down a new kind of physics in the middle of the night, and realizes that he might be holding the key to something enormous. So picture this. It's June 1925. Heisenberg has fled to Helgoland, this tiny rocky island about 50 kilometers off the German coast, basically a red sandstone cliff sticking out of the ocean. He's gone there because his hay fever is so bad on the mainland that he can barely think. His face is swollen, his eyes are streaming, and he figures the sea air might help. And it does, a little. Enough, at least, that he can work. And what he's working on is a question that has been eating at him for months. He wants to describe what happens inside an atom, but he's decided to throw away everything you can't actually see. Here's the thing about Heisenberg. He's not interested in picturing the atom. He doesn't care about orbits or little planetary models or trying to visualize what an electron is doing between measurements. He thinks that whole approach is a trap. You can't see an electron orbiting a nucleus. You've never watched one do it. All you can actually observe are the frequencies and intensities of the light that atoms emit and absorb. Those are the measurable quantities. So Heisenberg says, what if I build a theory that only talks about those things? What if I refuse to describe anything I can't directly measure? It sounds almost stubborn when you put it that way, but it's actually a deeply radical philosophical move. He's saying that physics should be a theory of observables, not a theory of hidden pictures. And on Helgoland, working through the night because he still can't sleep, he starts constructing a mathematical framework that does exactly that. He arranges the observable quantities, transition frequencies and amplitudes, into arrays, tables of numbers. And he discovers that when he multiplies these arrays together, the order matters. A times B does not equal B times A. Now, if you've ever done basic algebra, that feels wrong. 3 times 5 is the same as 5 times 3. That's how numbers work. But Heisenberg's quantities don't behave like ordinary numbers. They behave like something else entirely. And this is where his mentor, Max Born, back in Göttingen, recognizes what Heisenberg has stumbled onto. Born looks at these arrays and realizes they're matrices. They're objects from a branch of mathematics that most physicists at the time barely used. Matrix algebra, where multiplication is not commutative, where the order of operations genuinely matters. Born, along with his student Pascual Jordan, helps Heisenberg formalize the whole thing into what becomes known as matrix mechanics. And it works. It gives the right answers. You can use it to calculate the spectral lines of hydrogen, the energy levels of atoms, all the things that Bohr's model got right but couldn't fully justify. Matrix mechanics justifies them. But here's the problem. Almost nobody can understand it. The mathematics is dense, abstract, and deeply unintuitive. There's nothing to visualize. There's no picture of what the electron is doing. It's just these arrays of numbers obeying strange multiplication rules. And most physicists find it, honestly, kind of repulsive. Not because it's wrong, but because it feels alien. It doesn't look like physics as anyone had known it. And that's exactly the opening that Erwin Schrödinger walks through. Schrödinger is a very different character from Heisenberg. He's older, for one thing, already in his late 30s by this point. He's Austrian, cultured, a bit of a romantic in both his personal life and his scientific taste. He likes things he can picture. He likes continuous, smooth, classical-looking mathematics. And when he reads de Broglie's thesis about matter waves, the one we talked about earlier, he gets excited in a way that's almost aesthetic. If particles are waves, then there should be a wave equation governing them, something like the equations that describe sound waves or water waves or vibrating strings. Something elegant, something you can write down and almost feel. And in late 1925 and early 1926, Schrödinger finds it. The story goes that he retreats to a villa in the Swiss Alps, in Arosa, over the Christmas holiday, and in a burst of intense work, he derives what we now call the Schrödinger equation. It's one of the most important equations in the history of science, and it looks, at least on the surface, reassuringly familiar. It's a differential equation. It describes a wave function, this mathematical object usually written as the Greek letter psi, and it tells you how that wave function evolves over time and space. If you know the wave function at one moment, the equation tells you what it will be at the next moment. It's smooth, it's continuous, and it gives you something you can picture, a wave spreading through space, with peaks and troughs, with a shape you can draw. And when Schrödinger applies it to the hydrogen atom, it gives the exact same energy levels that Bohr's model predicted and that Heisenberg's matrix mechanics calculated. The same answers from a completely different mathematical starting point. Physicists are thrilled. Most of them vastly prefer Schrödinger's approach because they can actually understand it. They can work with it. It feels like real physics, like something connected to the classical tradition they grew up in. So now you have two theories of quantum mechanics, published within months of each other, built on completely different mathematical foundations, and both giving the same correct predictions. Matrix mechanics, abstract and algebraic. wave mechanics, smooth and visual. And the obvious question is, are they the same theory in different clothes? Or are they genuinely different? Schrödinger himself proves, in 1926, that the two formulations are mathematically equivalent. Every result you can get from one, you can get from the other. They're the same theory expressed in different languages. And that's a remarkable result. But here's where the real fight begins, because mathematical equivalence doesn't settle the question of what it all means. Schrödinger believes his wave function is physically real. He thinks the electron literally is a wave, spread out in space, and the wave function describes its actual physical shape. Heisenberg thinks that's nonsense. He thinks the wave function is a calculational tool, not a physical thing, and that trying to picture the electron as a literal wave is exactly the kind of false visualization that leads you astray. And standing somewhat between them, but increasingly on Heisenberg's side, is Niels Bohr. Remember Bohr, the man who built the first quantum model of the atom back in 1913? By the mid-1920s, Bohr has become something like the philosophical godfather of quantum mechanics. He runs his institute in Copenhagen, and the brightest young physicists in Europe come through his doors. He has an almost Socratic way of doing physics, talking endlessly, walking in circles, pushing ideas until they break, and he's deeply interested in the question that Schrödinger and Heisenberg are fighting over. What does the wave function mean? What is quantum mechanics actually telling us about reality? Now, Schrödinger's interpretation, the idea that the wave function is a real physical wave, runs into a serious problem almost immediately. Think about what happens when you actually detect an electron. You never find it spread out over a large region of space the way a wave would be. You always find it at a specific point. Click. Right there. The detector goes off in one spot. So if the electron is a wave before you measure it, what happens to the wave when you look? It seems to suddenly collapse from being spread out everywhere to being concentrated at a single location. Schrödinger doesn't like this. He finds it deeply unsatisfying, but he can't get around it. And this is where Max Born, the same Max Born who helped Heisenberg formalize matrix mechanics, makes one of the most consequential interpretive moves in the history of physics. In 1926, Born proposes that the wave function doesn't describe the electron itself. It describes the probability of finding the electron. Specifically, if you take the wave function at any point in space and square its absolute value, what you get is the probability that the electron will be found at that point. If you look, the wave function isn't a physical wave. It's a probability wave, a wave of likelihood. Think about what that means for a second. Before you measure the electron, all you have is a spread of probabilities. The electron isn't definitely here or definitely there. It's described by this smooth mathematical function that assigns different probabilities to different locations. And when you measure it, you get a definite result, but which result you get is genuinely random, weighted by those probabilities. You can't predict exactly where the electron will be. You can only predict the odds. This is not a limitation of your instruments. It's not that you're too clumsy to track the electron precisely. Born is saying that the randomness is fundamental. It's built into the fabric of reality at the quantum level. The universe, at its smallest scale, is not deterministic. It's probabilistic. And this is the idea that Einstein could never accept. You remember Einstein, the man who helped start all of this with the photoelectric effect, the man who endorsed de Broglie's matter waves? Einstein looked at Born's probability interpretation and said, famously, that God does not play dice with the universe. He couldn't believe that the deepest level of reality was governed by chance. He thought there had to be something underneath, some hidden layer of deterministic physics that quantum mechanics was failing to capture. And Bohr, gently but firmly, disagreed. Bohr believed the probabilistic description was complete. There was nothing hidden. The dice were real. That argument, Einstein versus Bohr, would continue for decades. It would play out in legendary debates at the Solvay conferences in Brussels, where the greatest physicists of the era gathered. Einstein would come armed with thought experiments designed to show that quantum mechanics was incomplete or inconsistent, and Bohr would stay up all night finding the flaw in Einstein's reasoning. Every time, Bohr won. Not because Einstein was wrong to be uncomfortable, but because every specific objection Einstein raised could be answered within the framework of quantum mechanics as it stood. But we're getting a little ahead of ourselves, because before the great debates, there's one more piece of the puzzle that Heisenberg is about to lay down, and it's the one that will become, for many people, the single most famous idea in all of quantum mechanics. It comes in 1927, and it starts with a deceptively simple question. If the electron is described by a wave function, and the wave function spreads out over space, then how precisely can you actually know where the electron is and how fast it's moving at the same time? Heisenberg works through the mathematics carefully, and what he finds is something genuinely shocking. Not just surprising, not just counterintuitive, but a result that seems to place a hard limit on what can ever be known about a particle. Not because our instruments aren't good enough, not because we haven't been clever enough, but because nature itself refuses to give you both answers at once. Here's what Heisenberg discovers. The more precisely you pin down a particle's position, the less precisely you can know its momentum, which is essentially its speed and direction. And the reverse is also true. The more precisely you know the momentum, the fuzzier the position becomes. This isn't a statement about technology. It's not about building a better microscope or inventing a more sensitive detector. It's a fundamental feature of reality at the quantum scale. There is a hard floor, a minimum amount of combined uncertainty that you can never get below, no matter what you do. Heisenberg expresses it mathematically. The uncertainty in position multiplied by the uncertainty in momentum is always at least as large as a tiny constant related to Planck's constant. Always, without exception. Let's sit with that for a second, because it's easy to hear it and think, okay, so our measurements are a little blurry. What's the big deal? But that's not what this is saying. In classical physics, in the world of Newton, every particle has a definite position and a definite momentum at every instant. You might not know what they are, but they exist. They're real numbers sitting there waiting to be discovered. Heisenberg's uncertainty principle says no. At the quantum level, a particle does not simultaneously possess a perfectly defined position and a perfectly defined momentum. It's not that the values are hidden. It's that they don't both exist as sharp, definite quantities at the same time. The universe doesn't have that information to give you, because the particle's state simply doesn't contain it. Think about what that means. For 300 years, physics had operated on the assumption that if you knew the position and momentum of every particle in the universe at one instant, you could, in principle, predict the entire future. That was the dream. Laplace, the great French mathematician, had said it explicitly back in the early 1800s. A sufficiently powerful intelligence, he argued, could take a snapshot of the universe and calculate everything that would ever happen. Heisenberg's uncertainty principle doesn't just make that dream difficult, it makes it impossible in principle. The snapshot Laplace imagined can never be taken. The information simply isn't there to be captured. Now, you might be thinking, okay, but why? Why should nature work this way? And this is where it connects beautifully back to something we talked about earlier. Remember de Broglie's matter waves? The idea that particles like electrons have a wavelength associated with them. Here's the thing about waves. If you have a wave that's spread out evenly, oscillating in a nice regular pattern across a large region of space, you can measure its wavelength very precisely. And wavelength is directly related to momentum. That's de Broglie's equation. So a spread-out wave means well-defined momentum. But where is that wave? Everywhere. It's not localized. You can't point to one spot and say the particle is right there. Now imagine the opposite. Suppose you want the particle to be localized, concentrated at a single point. To do that with waves, you have to add together many different wavelengths, all interfering constructively at one spot and destructively everywhere else, creating what physicists call a wave packet. You can make the packet very narrow, very localized. Great. Now you know where the particle is. But you've built that localized packet out of a huge range of different wavelengths, which means a huge range of different momenta. So the momentum is now deeply uncertain. This is not a quirk. It's a mathematical property of waves themselves. It's actually the same reason that a very short burst of sound, a click, contains a wide spread of frequencies, while a pure musical tone that has a single frequency has to ring on and on indefinitely. The uncertainty principle is baked into the wave nature of matter. It's not something Heisenberg imposed on the physics. It fell out of it inevitably, once you accepted that particles have wave-like properties. Heisenberg publishes this result in 1927, and it lands like a thunderclap. But here's what's really interesting about the human side of this story. Heisenberg and Bohr actually disagree about how to explain the uncertainty principle to the world. Heisenberg, in his original paper, uses a thought experiment involving a gamma-ray microscope. He imagines trying to observe an electron by bouncing a high-energy photon off it. The photon lets you see where the electron is, but the act of bouncing the photon off the electron gives the electron a random kick, disturbing its momentum. So the act of measurement itself creates the uncertainty. Heisenberg frames it as a disturbance problem. You can't observe without interfering. Bohr doesn't like this explanation. He thinks it's misleading because it suggests the electron had a definite position and momentum before you looked, and you just messed it up by looking. Bohr's view is deeper and, frankly, stranger. He argues that the electron doesn't have a definite position and momentum before the measurement. The uncertainty isn't created by the act of observation. It's inherent in the quantum state itself. The two men argue about this, apparently quite heatedly, and Heisenberg is reportedly brought to tears at one point during their discussions in Copenhagen. Eventually, Heisenberg adds a postscript to his paper, acknowledging Bohr's perspective, though the tension between them on this point never fully resolves. And this disagreement matters because it gets at the heart of what quantum mechanics is really telling us about the world. Is the fuzziness a practical limitation, something about the clumsiness of measurement? Or is it a statement about reality itself, that the universe at its smallest scale is genuinely, irreducibly uncertain? Bohr's answer, which becomes the backbone of what's called the Copenhagen interpretation, is the latter. Reality itself is fuzzy, until a measurement forces it to choose. Now, the Copenhagen interpretation. Let's talk about this, because it's the framework that most physicists ended up adopting, at least publicly, for most of the 20th century, and it's also the source of enormous philosophical discomfort that continues to this day. The Copenhagen interpretation is not a single crisp doctrine. It's more like a collection of principles that Bohr, Heisenberg, and Born assembled in the mid to late 1920s, mostly during their time together in Copenhagen, hence the name. The key ideas go something like this. The wave function, ESI, contains all the information you can have about a quantum system. Before you measure, the system doesn't have definite properties. It exists in a superposition, a combination of all possible states, each with an associated probability given by Born's rule. When you make a measurement, the wave function collapses. It snaps from a spread of possibilities into a single definite outcome. Which outcome you get is genuinely random, governed only by the probabilities, and you cannot ask what the system was doing before you measured it. That question, in the Copenhagen view, is meaningless. There is no deeper reality beneath the wave function. The wave function is the most complete description of the system that exists. Think about how radical that is. You're not just saying, we don't know what the electron is doing between measurements. You're saying the electron isn't doing anything definite between measurements. It doesn't have a position. It doesn't have a speed. Those properties come into existence only when you look. Before that, there's just the wave function, evolving smoothly according to Schrödinger's equation, carrying within it a cloud of possibilities. And here's the kicker. This interpretation works. It works spectacularly well. Every experiment you throw at it, the predictions come out right. The math is flawless. The Copenhagen interpretation gives you a recipe. Set up the wave function, evolve it, calculate the probabilities, compare with experiment, and it matches every time. But it also raises questions that have never been fully answered. What counts as a measurement? When exactly does the wave function collapse? Does it collapse when a detector clicks? When a human being looks at the detector? When the information reaches a conscious mind? Bohr was famously vague on this point. He drew a line between the quantum world and the classical world, what he called the cut, and said that measurement happens when a quantum system interacts with a classical measuring apparatus. But he never precisely defined where quantum ends and classical begins. And that ambiguity has haunted physics ever since. This is where Schrödinger, who by now is deeply unhappy with how his own equation is being interpreted, fires back with one of the most famous thought experiments in all of science. It's 1935, and Schrödinger is writing a paper about the state of quantum mechanics, and he's frustrated. He thinks the Copenhagen interpretation is absurd when you push it to its logical conclusion. So he constructs a scenario designed to make the absurdity vivid. Imagine, he says, a cat in a sealed box. Inside the box is a tiny bit of radioactive material, a Geiger counter, a vial of poison, and a mechanism that breaks the vial if the Geiger counter detects a radioactive decay. Radioactive decay is a quantum event. According to quantum mechanics, after a certain time, the atom is in a superposition of decayed and not decayed. If the Copenhagen interpretation is right, and the wave function doesn't collapse until a measurement is made, then the atom is in both states simultaneously. And since the cat's fate is linked to the atom, the cat is also in a superposition. The cat is both alive and dead at the same time until you open the box and look. Schrödinger didn't propose this because he thought cats could actually be alive and dead simultaneously. He proposed it because he thought it was ridiculous, and he wanted to show that the Copenhagen interpretation, taken seriously, led to conclusions that no sensible person could accept. It was a reductio ad absurdum, a protest. But here's what's fascinating. The thought experiment didn't destroy the Copenhagen interpretation. Instead, it became the most famous illustration of quantum superposition in popular culture. People remember the cat. They remember the alive and dead thing. And many physicists simply shrugged and said, yes, that's how it works at the quantum level. But decoherence, the interaction of the quantum system with its environment, effectively collapses the superposition long before you get to anything as large as a cat. The cat is never really in a superposition in practice because the box isn't perfectly sealed from the rest of the universe. The quantum weirdness gets washed out by the sheer complexity of a macroscopic system, interacting with trillions of air molecules and photons and vibrations. But that answer, while practically satisfying, doesn't fully resolve the philosophical question. It pushes the mystery back a step. Where exactly does the superposition end? At what scale does quantum become classical? That question, believe it or not, is still open. Physicists argue about it today, right now, in the 21st century. The measurement problem, as it's called, remains one of the deepest unsolved puzzles in the foundations of physics. And it's worth noting that Einstein never stopped pushing on this. He never accepted the Copenhagen interpretation. In 1935, the same year, Schrödinger proposed his cat, Einstein, co-authored a paper with two younger physicists, Boris Podolsky and Nathan Rosen, that would become one of the most cited papers in the history of physics. It's known as the EPR paper, after their initials, and it introduces a concept that Einstein called spooky action at a distance. The argument goes like this. Imagine two particles that interact and then fly apart in opposite directions. Quantum mechanics says their properties are correlated in a very specific way. They're entangled so that measuring one instantly tells you something about the other, no matter how far apart they are. Einstein argued that this meant either quantum mechanics was incomplete, missing some hidden variables that predetermined the outcomes, or it required information to travel faster than light, which violated relativity. Either way, he said, something was wrong with the theory. Bohr responded, as he always did, with a careful and somewhat opaque argument that the question itself was poorly framed. Bohr's reply to the EPR paper came quickly, within months, and it was dense, it was subtle, and honestly, it was not entirely clear even to many physicists who read it at the time. What Bohr essentially argued was that Einstein was making an unjustified assumption that you could talk about the properties of a particle as if they existed independently before you measured them. Bohr said no. The two entangled particles aren't two separate things with two separate sets of hidden properties waiting to be revealed. They're part of a single quantum system, and you can't meaningfully separate them until a measurement is actually performed. The correlation between them isn't information traveling from one to the other. It's a feature of the whole system, a wholeness that doesn't have a classical analogy. Now, if that sounds a little slippery to you, you're in good company. A lot of physicists at the time felt the same way. Einstein certainly did. He found Bohr's response unsatisfying, almost evasive. And the two men, who had genuinely respected each other for decades, who had exchanged warm letters and visited each other's homes, who had spent long evenings debating the nature of reality over cups of tea. They never really reconciled on this point. Einstein went to his grave in 1955 believing that quantum mechanics was incomplete, that there had to be a deeper layer underneath, some set of hidden variables that would restore the determinism and the local realism he felt the universe required. And Bohr, who died in 1962, maintained to the end that Einstein was simply wrong, that the desire for a classical picture underneath quantum mechanics was a kind of nostalgia for a world that didn't exist at the quantum level. Here's the thing, though. For about 30 years after the EPR paper, the whole debate was considered mostly philosophical. It was a disagreement about interpretation, about what quantum mechanics meant, not about what it predicted. Both sides agreed on the math. Both sides agreed on what the experiments would show. The argument was about the story you told around the math. And in physics, if two views give the same predictions, there's no experiment to settle the fight. So most working physicists just shrugged and moved on. They used the equations. They built things. They made predictions that turned out to be spectacularly correct. And they left the philosophy to the philosophers. There's a famous phrase that captures this attitude. It's sometimes attributed to Richard Feynman, sometimes to others, but it goes, "Shut up and calculate." And that was, for a generation, the dominant culture in physics. Don't ask what the wave function means, just use it. But then something remarkable happened. In 1964, a quiet, unassuming Irish physicist named John Stuart Bell, working at CERN in Geneva, published a short paper that changed everything. And I mean everything. Bell did something that Einstein, Bohr, and everyone else had assumed was impossible. He found a way to turn the philosophical debate into an actual experiment. Let's slow down here, because this is one of those moments that deserves real space. Bell's theorem, as it came to be known, is one of the most profound results in the history of physics, and yet most people have never heard of it. Bell asked a very precise question. He said, "Okay, let's take Einstein's side seriously for a moment. Let's assume that the particles in an EPR experiment really do have definite properties before you measure them, hidden variables, and that any correlation between them is established locally at the moment they interact, with no faster-than-light influence afterward. If that's true," Bell showed, "then the statistical correlations you'd see in your measurements would have to obey a certain mathematical limit." He derived an inequality, a ceiling on how strongly correlated the results could be under any local hidden variable theory. And then he showed that quantum mechanics predicts correlations that exceed that ceiling. Think about what that means. Bell wasn't saying Einstein was wrong because of philosophy. He was saying that if Einstein was right, if hidden variables existed and everything was local, then the numbers in the experiment would come out one way. And if quantum mechanics was right, the numbers would come out a different way. The two options made different predictions. You could actually test it. Now, Bell published this in 1964, but the technology to do the experiment properly didn't exist yet. You needed to be able to create pairs of entangled particles, send them flying apart to distant detectors, and measure their properties with very precise timing, all while making sure no signal could possibly travel between the two detectors fast enough to influence the results. That's a hard experiment. It took almost 20 years before someone pulled it off convincingly. The person who did it, the one whose name is most associated with the first really rigorous test, was a French physicist named Alain Aspect. In 1981 and 1982, working at the University of Paris-Sud in Orsay, Aspect and his team performed a series of experiments using pairs of entangled photons. They set up their detectors far enough apart and switched the measurement settings quickly enough that no signal traveling at the speed of light could have gotten from one detector to the other in time to affect the outcome. And the results were clear. The correlations violated Bell's inequality. They matched the predictions of quantum mechanics, not the predictions of any local hidden variable theory. Einstein was wrong, or more precisely, the specific hope that Einstein had championed, that you could explain quantum correlations with local hidden variables, that there was some deeper deterministic layer underneath that respected locality, that hope was ruled out by experiment. Nature itself had spoken, and it said, no, you can't have both local realism and the results we actually see. Now let's be careful here, because this is subtle, and it matters. What Bell's theorem and Aspect's experiment ruled out was the combination of two things: hidden variables and locality. You could still have hidden variables if you were willing to give up locality, meaning you'd accept that influences can travel faster than light in some sense. And in fact, there is a version of quantum mechanics that does exactly that. It was developed by the physicist David Bohm back in 1952, a pilot wave theory where particles have definite positions at all times, but are guided by a wave that responds instantaneously to distant events. Bohm's theory reproduces all the predictions of standard quantum mechanics, but it's explicitly non-local. Most physicists find it inelegant, or at least uncomfortable, but it's never been ruled out by experiment. It's a perfectly valid interpretation. It just trades one kind of weirdness for another. And here's the kicker. Even though entangled particles show these spooky correlations, you can't actually use entanglement to send a message faster than light. This is a crucial point, and it's one of those things that sounds contradictory until you think about it carefully. When you measure your particle and it comes out, say, spin up, the distant particle instantly becomes spin down. But all you see on your end is a random result. You can't control whether you get spin up or spin down. It's random. And the person at the other end sees a random result too. It's only when you later compare your lists of results, which you have to do through a normal, slower-than-light communication channel, that you see the correlations. The correlations are real, but they can't carry information on their own. So relativity is safe. No messages travel faster than light. But the underlying reality is, in some deep sense, non-local. The universe is more connected than classical physics ever imagined. Alain, Aspect by the way, along with John Clauser and Anton Zeilinger, received the Nobel Prize in Physics in 2022 for this work, 2022. Think about that timeline. Bell published his theorem in 1964. Aspect did his experiments in the early 1980s, and the Nobel Committee waited until 2022 to award the prize. That gives you a sense of how long it took for the physics community to fully absorb the implications of what Bell had uncovered. For decades, this was considered a niche topic, something for the philosophically inclined fringe. The mainstream attitude was still, shut up and calculate. But slowly, steadily, the significance of Bell's result seeped into the culture of physics, and by the time the Nobel was awarded, entanglement had become not just a philosophical curiosity, but a practical resource. Because here's what happened in the meantime. While the philosophers and the foundations of physics people were arguing about what entanglement meant, a whole new generation of physicists and engineers started asking a different question. What can you do with it? And the answer turned out to be extraordinary. In 1984, Charles Bennett and Gilles Brassard proposed a protocol for quantum key distribution, a way to use quantum mechanics to create perfectly secure communication channels. The idea relies on the fact that you can't measure a quantum state without disturbing it, so any eavesdropper would inevitably leave a trace. Then in 1993, Bennett and a group of collaborators showed that entanglement could be used for quantum teleportation, not teleporting matter like in science fiction, but transferring the exact quantum state of one particle to another particle far away, destroying the original in the process. And in 1994, a mathematician at Bell Labs named Peter Shor showed that a hypothetical quantum computer, one that could manipulate qubits in superposition and entanglement, could factor large numbers exponentially faster than any classical computer. That result sent shockwaves through the world of cryptography because the security of most modern encryption depends on the assumption that factoring large numbers is practically impossible. A working quantum computer would break that assumption wide open. All of these developments, quantum cryptography, quantum teleportation, quantum computing, they all trace directly back to the ideas that Einstein, Podolsky, and Rosen raised in 1935, and that Bell clarified in 1964. The very feature of quantum mechanics that Einstein found most troubling, entanglement, turned out to be one of its most powerful resources. There's a deep irony in that, and I think Einstein would have appreciated it, even if he wouldn't have liked it. But let's come back to the deeper question, the one that's been running underneath all of this like an underground river. What does quantum mechanics actually tell us about the nature of reality? Because the experiments are settled, the math works, the technology is being built. But the interpretation, the story we tell about what's really going on underneath the equations, that remains genuinely unresolved. And by the middle of the 20th century, the Copenhagen interpretation wasn't the only game in town anymore. Alternatives were emerging, each one stranger and more ambitious than the last. And the most famous of them, the one that still provokes arguments at physics conferences and dinner parties alike, came from a young graduate student at Princeton who had the audacity to disagree with Niels Bohr. His name was Hugh Everett, and his idea was as radical as anything quantum mechanics had ever produced. He wanted to take the math seriously, all of it, and what the math told him was that the universe splits. Now, let's slow down here, because that sounds like science fiction, and I want you to understand why it's not. Or at least, why it's not obviously science fiction. Hugh Everett was not some crank on the margins. He was a brilliant young physicist working under John Wheeler at Princeton in the mid-1950s, and Wheeler was one of the most respected theoretical physicists in the world, a man who had worked with Bohr himself in Copenhagen. Everett's starting point was simple, and in a way, it was the most conservative move possible. He looked at the Schrödinger equation, that beautiful wave equation we talked about earlier, the one that describes how quantum systems evolve over time, and he asked a question that nobody had satisfactorily answered. Why do we need two rules? Here's what he meant. In the standard Copenhagen picture, quantum mechanics has this awkward split. When no one is looking, a quantum system evolves smoothly and continuously according to the Schrödinger equation. The wave function spreads out, it explores all possibilities. It's this elegant mathematical object flowing through time. But then, the moment someone makes a measurement, a completely different rule kicks in. The wave function collapses. All those possibilities vanish except one, and you get a definite result. Born's rule tells you the probability of each outcome, and Copenhagen tells you not to ask what was happening before you looked. Everett thought this was ugly, and honestly, he had a point. Think about it. You've got one rule for when nobody's watching and a completely different rule for when someone is. But what counts as a measurement? What counts as an observer? A human being? A cat? A Geiger counter? A grain of dust? Copenhagen never really answered that question cleanly. It just drew a line between the quantum world and the classical world and said, "Don't worry about where exactly the line is." Everett found that deeply unsatisfying. So here's what he proposed, and it's breathtakingly simple in its logic, even if its implications are staggering. What if there is no collapse? What if the Schrödinger equation is the only rule, and it applies everywhere, all the time, to everything, including observers, including measurement devices, including you and me? What happens then? Well, let's think it through. Say you have an electron in a superposition of spin up and spin down. In Copenhagen, when you measure it, the wave function collapses and you get one result. But in Everett's picture, there's no collapse. Instead, when you interact with the electron, when your measuring device couples to it, you become entangled with it. The combined system, you plus the electron, enters a superposition. In one branch of that superposition, you measured spin up, and you're aware of having measured spin up. In the other branch, you measured spin down, and you're aware of having measured spin down. Both outcomes happen. Both versions of you are real, but they can no longer interact with each other because they've decohered, they've become effectively separate. And this is where people's eyes either light up or glaze over, because the implication is enormous. Every quantum event that has multiple possible outcomes doesn't pick one. They all happen, each in its own branch of an ever-splitting universal wave function. The universe, in this picture, is not a single thread of history. It's a vast, incomprehensibly vast tree of branching realities, all equally real, all coexisting in the mathematics of one gigantic wave function that never, ever collapses. Everett called this the relative state formulation. The name many worlds came later, popularized by the physicist Bryce DeWitt in the 1970s. Everett himself was more restrained in his language, but the idea was the same. There is no special role for the observer. There is no collapse. There is just the wave function of the universe, evolving according to one rule, forever. Now, you might be thinking, that's insane. And you wouldn't be alone. When Everett submitted his doctoral thesis in 1957, the reaction was, let's say, muted. Wheeler, his advisor, believed the work was important, but he also knew it would be controversial, and he tried to soften it. He actually arranged for Everett to visit Bohr in Copenhagen to discuss the idea. And by all accounts, the visit did not go well. Bohr and his circle were not interested. They didn't engage with the argument on its merits so much as dismiss it. The prevailing attitude was something like, "We've already solved this problem, and this young man simply doesn't understand complementarity." Everett was deeply discouraged. He had hoped for a serious debate, a real engagement with the logical structure of his argument, and instead, he got a polite brush-off from the establishment. After finishing his PhD, he left academic physics entirely. He went into defense analysis and operations research, working for the Pentagon on classified projects. He never returned to quantum foundations. He died in 1982, at just 51 years old, largely unrecognized for what many physicists today consider one of the most important ideas in the history of the field. And here's what's poignant about that. By the time Everett died, his interpretation was just beginning to gain serious traction. DeWitt's advocacy in the 1970s had brought many worlds to a wider audience, and a new generation of physicists was starting to take it seriously. Today, If you survey physicists who work on quantum foundations, many worlds is one of the most popular interpretations. Some polls put it neck and neck with Copenhagen. It's not fringe anymore. It's one of the leading contenders. But let's be honest about what makes people uncomfortable with it, because the discomfort is real, and it's worth sitting with. Many worlds asks you to accept that there are an unimaginably large number of copies of you, right now, living slightly different lives in branches of the universal wave function that split off every time a quantum event occurs. Every photon that hits a beam splitter, every radioactive atom that does or doesn't decay, every electron that goes left or right, each of these spawns new branches. The number of branches is not just large, it's beyond anything you can visualize. It makes the number of atoms in the observable universe look tiny by comparison. And here's the thing, you can never access those other branches. You can never communicate with them. You can never detect them. The decoherence that separates them is, for all practical purposes, absolute and irreversible. So in a very real sense, many worlds makes no different predictions from standard quantum mechanics. The math is the same. The probabilities come out the same. The experiments give the same results. The only difference is the story you tell about what's happening underneath. And that raises a genuinely deep philosophical question. If a theory postulates an infinite number of unobservable parallel realities, and those realities make no measurable difference to anything you can ever test, is that theory more parsimonious or less parsimonious than one that just says the wave function collapses? Everett's supporters argue it's actually simpler because it has fewer rules. One equation, no collapse, no mysterious observer. The complexity is in the ontology, in how much stuff exists, but the laws themselves are cleaner. Critics argue that simplicity in laws doesn't help much if you're postulating more reality than anyone can comprehend. This is not a settled argument. And I want to be clear about that, because sometimes popular science writing makes it sound like many worlds is either obviously true or obviously crazy, and neither of those is fair. It's a serious interpretation held by serious physicists, and it has genuine advantages. It takes the math at face value. It doesn't require a mysterious collapse mechanism. It doesn't need to define what counts as a measurement. But it also has genuine problems, particularly around probability. If every outcome happens, what does it even mean to say that one outcome is more probable than another? Everett and his followers have proposed answers to this, some of them quite clever, involving decision theory and rational betting strategies in a branching universe, but not everyone finds them convincing. So many worlds is one path. But it's not the only alternative to Copenhagen that emerged in the second half of the 20th century. Let's talk about another one, because it approaches the problem from a completely different direction, and it's one of the most creative ideas in all of physics. In the 1980s, a group of physicists began developing something called decoherence theory in a much more rigorous way. We touched on decoherence earlier, the idea that quantum superpositions become effectively classical when a system interacts with its environment. But in the 1980s and 1990s, physicists like Wojciech Zurek and Dieter Zeh worked out the details with real mathematical precision, showing exactly how the environment selects certain states, so-called pointer states, as the ones that survive and appear classical. This framework, sometimes called quantum Darwinism in Zurek's version, explains why we see cats that are alive or dead, but never both. The environment is constantly monitoring quantum systems, and that monitoring process destroys the delicate interference patterns that would reveal superposition. It's not that collapse happens because a conscious observer looks. It's that the environment is always looking, in a sense, and the universe is always decohering. Now, decoherence is not really an interpretation by itself. It's a physical process, and it's accepted across almost all interpretations. Many worlds uses it. Consistent histories uses it. Even modern versions of Copenhagen incorporate it. But what decoherence doesn't do, and this is crucial, is solve the measurement problem entirely. It explains why you don't see superpositions in everyday life. It explains the appearance of collapse. But it doesn't tell you whether the other branches are real, as many worlds claims, or whether they genuinely disappear, as Copenhagen would have it. Decoherence narrows the question, but it doesn't close it. And then there are even more exotic approaches. There's the idea of quantum Bayesianism, or cubism, developed in the early 2000s by Christopher Fuchs, Rüdiger Schack, and others. Cubism says something quite radical. It says the wave function isn't a description of objective reality at all. It's a description of an agent's personal beliefs about what will happen when they interact with the world. Probabilities in quantum mechanics are not frequencies out there in nature. They're degrees of belief, like a gambler's odds, updated through experience. In cubism, quantum mechanics is a user's manual for navigating an uncertain world, and the question, what is really happening when no one is looking, is simply not a question the theory is designed to answer. It sounds like giving up, but cubists would disagree. They'd say they're being honest about what the theory actually gives us, which is a set of rules for making predictions, not a God's eye description of reality. And they'd point out that trying to tell a story about what's really happening is exactly what leads to all the paradoxes and confusion. Just use the tool. Trust the tool. Don't ask the tool to be a mirror of ultimate reality. Whether you find that liberating or frustrating probably says something about your philosophical temperament, and that's actually one of the most fascinating things about the interpretation debate. It has persisted for nearly a century now, not because physicists are confused about the math or the experiments, those are clear, but because the math seems to underdetermine the story. Multiple interpretations are consistent with all known data, and choosing between them involves questions that physics alone may not be equipped to answer. Questions about what counts as real, what counts as an explanation, what role observers play in the universe they observe. And this brings us to something that I think is genuinely profound, something worth sitting with as you settle deeper into the quiet of this moment. Quantum mechanics is, by any measure, the most successful physical theory ever constructed. Its predictions have been confirmed to extraordinary precision, in some cases to 12 decimal places. It underpins the technology in the device you're listening to right now. Transistors, lasers, LEDs, MRI machines, GPS satellites, all of it depends on quantum mechanics being correct. And yet, after more than 100 years, the people who understand it best still cannot agree on what it means, what it actually says about the world. And that fact, that stubborn, irreducible fact, is itself one of the most important things quantum mechanics has taught us. So, let's talk about where all of this has led, not just philosophically, but practically. Because while the interpretation debate has been simmering in seminar rooms and philosophy departments, the physics itself has been marching forward in ways that would have astonished the founders. And the story of quantum mechanics in the late 20th and early 21st century is, in many ways, a story about learning to use the strangeness rather than just argue about it. Think back to entanglement for a moment. When Einstein first flagged it in 1935, he thought he was pointing out a flaw, a reductio ad absurdum that proved quantum mechanics must be incomplete. When Bell wrote his theorem in 1964, it was a piece of pure theory, a thought experiment with inequality signs. When Aspect ran his experiments in the early 1980s, it was cutting-edge physics, but still, fundamentally, a test of foundations. Nobody was thinking about building anything with entanglement. It was too weird, too fragile, too far from engineering. But here's what happened. Starting in the 1990s, a handful of physicists and computer scientists began to realize that entanglement wasn't just a philosophical curiosity. It was a resource, something you could use. And that shift in perspective, from entanglement as a paradox to entanglement as a tool, is one of the most consequential intellectual moves of the last 50 years. The quantum computing story really crystallizes this. We touched on Shor's algorithm earlier, Peter Shor's 1994 discovery that a quantum computer could factor large numbers exponentially faster than any known classical method. But let's slow down and appreciate why that mattered so much. The entire infrastructure of digital security, the encryption that protects your bank account, your medical records, your private messages, rests on the assumption that factoring very large numbers is practically impossible for classical computers. A 2048-bit encryption key would take a classical supercomputer longer than the age of the universe to crack by brute force. Shor showed that a sufficiently powerful quantum computer could do it in hours, maybe minutes. Now, when Shor published this, there were no quantum computers capable of doing anything useful. The largest quantum systems anyone had built could handle maybe a couple of qubits, quantum bits, and they were incredibly noisy and unstable. So in one sense, Shor's algorithm was a theoretical bombshell with no practical fuse. But it galvanized an entire field. Suddenly, governments and corporations and research labs around the world had a concrete, almost terrifyingly concrete, reason to care about quantum computing. The race was on. And here's where the physics gets genuinely beautiful. A qubit, unlike a classical bit, doesn't have to be 0 or 1. It can exist in a superposition of both. And when you entangle multiple qubits together, the number of states they can simultaneously explore grows exponentially. 2 qubits can represent 4 states at once. 10 qubits can represent over 1,000. 50 qubits can represent more states than there are atoms in a human body. 300 qubits can represent more states than there are atoms in the observable universe. That exponential scaling is the source of quantum computing's power, and it comes directly from superposition and entanglement, the very features that made the founders so uncomfortable. But building a quantum computer is, to put it mildly, extraordinarily difficult. And the reason it's difficult connects back to something we talked about earlier: decoherence. Remember how Zurek and Zeh showed that quantum superpositions are incredibly fragile, that any interaction with the environment causes the delicate phase relationships to leak away, effectively collapsing the quantum state into something classical? Well, that's exactly the enemy of quantum computation. Every qubit has to be isolated from its environment with almost absurd precision. Many of the leading approaches use superconducting circuits cooled to temperatures colder than outer space, around 15 millikelvins, just a hair above absolute zero. Others trap individual ions with electromagnetic fields in ultra-high vacuum chambers. Some use photons threaded through optical circuits. Each approach has its own engineering nightmares. And then there's error correction, which is its own fascinating story. Classical computers deal with errors easily. If a bit flips from 0 to 1, you just check it against a redundant copy. But in quantum computing, you can't simply copy a qubit. There's actually a theorem that forbids it, the no-cloning theorem, which follows directly from the linearity of quantum mechanics. So quantum error correction has to work in a completely different way. In encoding logical qubits across many physical qubits in clever patterns that allow you to detect and correct errors without ever directly measuring the quantum state and destroying it. It's like performing surgery on a patient you're not allowed to look at. The fact that it's possible at all is remarkable, and it was only proven in the mid-1990s by Shor and independently by Andrew Steen. As of the early 2020s, companies like Google, IBM, and several startups have built quantum processors with a few hundred qubits. In 2019, Google claimed to have achieved what they called quantum supremacy, using a 53-qubit processor called Sycamore to perform a specific calculation in about 200 seconds that they estimated would take the world's fastest classical supercomputer roughly 10,000 years. That claim was debated. IBM pushed back, arguing that with clever classical techniques the gap wasn't quite so dramatic. But the broader point stood. Quantum computers were beginning to do things that classical computers genuinely struggled with. Now we're still far from a fully fault-tolerant, large-scale quantum computer. The machines that exist today are what researchers call noisy, intermediate-scale quantum devices. They're powerful enough to be interesting, but too error-prone to run the algorithms that would really change the world, like Shor's algorithm applied to real encryption keys. That probably requires millions of physical qubits, and we're not there yet. But the trajectory is real, and the investment is enormous. And the whole enterprise rests on taking quantum mechanics seriously at its most counterintuitive. Superposition isn't a metaphor. Entanglement isn't a paradox to be explained away. They're engineering specifications. But quantum computing isn't the only place where the strangeness has become practical. Let's talk about quantum sensing for a moment, because it's a beautiful example of turning a supposed limitation into an advantage. Remember the uncertainty principle? Heisenberg showed that you can't simultaneously know a particle's position and momentum with arbitrary precision. That sounds like a restriction, and it is. But it also means that quantum systems are exquisitely sensitive to tiny disturbances. If you prepare an atom in a carefully controlled quantum state, any interaction with an external field, a magnetic field, a gravitational gradient, even the faint tug of a passing mass, will shift that state in a measurable way. Atomic clocks work on this principle. The best atomic clocks today, using strontium or ytterbium atoms trapped in optical lattices, are so precise that they would neither gain nor lose a second in 15 billion years, roughly the age of the universe. That precision comes directly from quantum mechanics. And those clocks aren't just for timekeeping. They're sensitive enough to detect differences in gravitational potential over a height change of just a centimeter, which means they can be used for geodesy, mapping the Earth's gravitational field with extraordinary resolution. They can detect underground tunnels, mineral deposits, shifts in water tables. The uncertainty principle, that thing Einstein found so troubling, is now a precision instrument. And then there's quantum cryptography, which we mentioned briefly before. Quantum key distribution, or QKD, uses the fact that measuring a quantum state disturbs it to create communication channels that are, in principle, provably secure. If an eavesdropper tries to intercept the quantum states being exchanged between two parties, the disturbance is detectable. The laws of physics themselves guarantee the security, not the computational difficulty of some math problem. China launched a satellite called MISSIS in 2016, specifically to test quantum key distribution over long distances, and they've demonstrated entanglement-based communication across more than 1,000 kilometers. It works, The physics that Bohr and Einstein argued about in hotel lobbies in the 1930s is now being engineered into communication infrastructure. So here's the thing that I find genuinely remarkable. All of these technologies, quantum computing, quantum sensing, quantum cryptography, they work. They work because quantum mechanics works. The predictions are correct. The engineering succeeds when it follows the theory. And yet, as we've spent this whole journey discussing, nobody agrees on what the theory means. The engineers building quantum computers don't need to choose between Copenhagen and many worlds, and pilot waves and cubism. The math is the same in every interpretation. The qubits don't care about your philosophy. And this is actually a clue, I think, about the nature of the problem. The fact that the interpretations are empirically equivalent, that no experiment has ever distinguished between them, suggests that the disagreement might not be a physics problem at all. It might be a philosophy problem that happens to live inside physics. And that's not a dismissal. Philosophy matters. The question of what's real, what exists, what it means for something to happen, these are among the deepest questions human beings have ever asked. Quantum mechanics just happens to be the place where those questions became unavoidable for working scientists. There's a wonderful quote, often attributed to Richard Feynman, though the exact wording varies, that goes something like, "If you think you understand quantum mechanics, you don't understand quantum mechanics." It's become a cliché, but there's a real insight buried in it. The theory resists the kind of understanding we're used to. We want a picture. We want to be able to close our eyes and visualize what's happening. And quantum mechanics seems to be telling us that the universe, at its most fundamental level, doesn't work the way our evolved primate brains expect it to. The wave function isn't a thing you can see. Superposition isn't a state you can imagine. Entanglement isn't a connection you can draw on a map. These are mathematical structures that make perfect predictions about experimental outcomes, but they don't map onto any familiar picture of reality. And maybe that's okay. Maybe that's even beautiful, because it means the universe is stranger and more interesting than we could have guessed. It means there are layers to reality that we can touch with our mathematics, but not with our intuition. And the fact that we've managed to reach those layers at all, that a species that evolved to track predators on a savanna and throw rocks at prey has somehow figured out the rules governing atoms and photons and the vacuum of space, that's one of the most astonishing things that has ever happened. Which brings us to something that's been quietly lurking behind everything we've discussed, a question that might be the deepest one of all. And it's a question that connects the interpretation debate to the largest possible canvas, the universe itself. Because if quantum mechanics is truly fundamental, if it really does govern everything, then it doesn't just apply to electrons and photons and atoms. It applies to stars, to galaxies, to the entire cosmos. And that raises a question that nobody saw coming when quantum mechanics was first being assembled in those cramped offices in Copenhagen and Göttingen. If the wave function describes everything, then what is the wave function of the entire universe? And who or what collapses it? Think about that for a second. In the standard Copenhagen picture, you have a system, an electron, a photon, whatever, and you have an observer who measures it. The measurement causes the wave function to collapse, and you get a definite result. Fine. That works beautifully in a laboratory. But now, zoom out, way out. If the entire universe is a quantum system, and it is because it's made of quantum stuff, then the universe has a wave function too. A single, enormous, incomprehensibly complex wave function that encodes every particle, every field, every possible configuration of everything. So here's the problem. Who's outside the universe to observe it? Who collapses the wave function of the cosmos? There's no external observer. There can't be. By definition, the universe is everything. There's no outside. This is the problem that drove a physicist named John Wheeler to think very carefully about cosmology and quantum mechanics together, starting in the 1960s. Wheeler, who we've brushed past before, was the same person who mentored Hugh Everett and who coined the term black hole. He had this remarkable ability to ask questions that sounded almost childlike in their simplicity, but turned out to be devastatingly deep. And one of the questions he kept asking was this: does the universe exist if nobody is looking at it? Now that sounds like a late-night dorm room question, but Wheeler meant it technically. If quantum mechanics requires observation to produce definite outcomes, and if the early universe had no observers, no conscious beings, no measurement devices, then in what sense did the early universe have definite properties? Was it all just a vast superposition, a fog of possibilities, until something came along to look? Wheeler developed an idea he called the participatory universe. The notion, loosely, is that observers aren't passive witnesses to reality. They're participants in creating it, not in a mystical sense, but in the specific, quantum mechanical sense that the act of measurement brings definiteness out of possibility. And he pushed this further than most physicists were comfortable with. He suggested that observations made today might, in some sense, reach back and give shape to events that happened billions of years ago. He illustrated this with a thought experiment called the delayed choice experiment, which we won't get deep into, but the basic idea is that you can set up a situation where a photon seems to decide whether it traveled as a wave or a particle only after it's already completed its journey, based on what measurement you choose to make at the end. And this has actually been confirmed experimentally. It's real. It doesn't let you send messages backward in time or anything like that, but it does suggest that the past isn't quite as fixed and settled as we'd like to believe, at least not at the quantum level. Now, most working physicists don't go as far as Wheeler did, but the question he raised, what is the quantum state of the whole universe, became the foundation of an actual field, quantum cosmology. And in 1983, two physicists, James Hartle and Stephen Hawking, proposed something remarkable. They wrote down what they called the no-boundary proposal, sometimes called the Hartle-Hawking state. The idea, put as simply as I can manage, is that the universe doesn't have a boundary in time. It doesn't have a sharp beginning, a moment of creation where time suddenly starts ticking. Instead, as you go further and further back toward what we'd call the Big Bang, time itself gradually becomes indistinguishable from space. It rounds off smoothly, the way the surface of a sphere doesn't have an edge. There's no point where it begins. It just is. And here's what's wild about this. Hartley and Hawking were applying quantum mechanics, specifically the path integral formulation that Richard Feynman had developed decades earlier, to the entire universe. Feynman's path integral says that to calculate the probability of a quantum system going from state A to state B, you have to sum over every possible path it could take, weighted by a phase factor. Every path contributes. Most of them cancel out, but the sum of all of them gives you the right answer. Hartley and Hawking did this for the geometry of space-time itself. They summed over every possible shape the universe could have, every possible geometry, to calculate the wave function of the cosmos, the wave function of the universe. That phrase alone should give you a little vertigo if you sit with it. A single mathematical object that encodes every possible configuration of everything that exists. Now, whether the no-boundary proposal is correct is very much an open question. There are competing ideas. Alexander Vilenkin proposed a tunneling from nothing model around the same time, where the universe quantum tunnels into existence from literally nothing. The way a particle can tunnel through a barrier, it classically shouldn't be able to cross. Both proposals are speculative. Both are mathematically interesting. Neither has been confirmed. But what matters for our purposes is the sheer ambition of the question. Quantum mechanics, this theory that started with Max Planck trying to fix a problem with the color of hot metal, has grown to the point where physicists are using it to ask how the universe itself came into being. The same framework that explains why your phone screen glows is being applied to the origin of space and time. That's an extraordinary arc, and it connects to something else that's been simmering in theoretical physics for decades: the relationship between quantum mechanics and gravity. This is, arguably, the biggest unsolved problem in all of physics. We have quantum mechanics, which governs the very small. We have general relativity, Einstein's theory of gravity, which governs the very large, the curvature of space-time around stars and galaxies and black holes. Both theories are spectacularly successful in their own domains, but they don't fit together. When you try to apply quantum mechanics to gravity the way you'd apply it to electromagnetism, you get nonsensical answers. Infinities that can't be removed, calculations that blow up, the mathematics breaks. This isn't just a technical inconvenience. It means there are situations in nature where both theories should apply simultaneously, and we don't have the tools to describe them. The interior of a black hole, for instance, where gravity is incredibly strong and the relevant scales are incredibly small. Or the very earliest moments of the Big Bang, when the entire observable universe was compressed into a region smaller than an atom. In those regimes, you need a theory of quantum gravity, a framework that combines both. And we don't have one. Not yet. String theory is one attempt. It proposes that the fundamental constituents of reality aren't point particles but tiny vibrating strings, and it naturally incorporates gravity. It's mathematically rich, almost dizzyingly so, but it hasn't made any testable predictions that we can currently check. Loop quantum gravity is another approach, which tries to quantize space-time itself, treating space as being made of discrete, tiny loops woven together like a fabric. It's less flashy than string theory, but has its own elegance. There are other approaches too. Causal set theory. Asymptotic safety. Each takes a different guess about what the fundamental structure of space-time really is. But here's the thing that connects all of this back to our story. Every single one of these approaches to quantum gravity has to grapple with the same interpretive questions we've been talking about all night. What does the wave function mean? What counts as a measurement? Does superposition apply to space-time itself? Can space be in two different shapes at once? If the many worlds interpretation is right, then every quantum event in the history of the universe has spawned branches, and the geometry of space-time itself might be branching. If Copenhagen is right, then something has to collapse the wave function of the cosmos, and we're back to Wheeler's question about who's watching. The interpretation debate isn't just philosophy. It feeds directly into the deepest questions in physics. And maybe that's the most important thing to take away from all of this. Quantum mechanics isn't finished. It's not a closed book. It's not a chapter of physics that was wrapped up in the 1930s and shelved. It's alive. Physicists are arguing about it right now, today, in 2024, with the same intensity that Bohr and Einstein brought to their debates in the 1930s. The questions have evolved, the mathematics has gotten more sophisticated, the experiments are more precise, but the core mystery remains. What is the nature of reality at the deepest level? And why does it behave so differently from anything we'd expect? You know, there's a tendency when people first encounter quantum mechanics to feel like it's impossibly confusing, like it's a subject reserved for geniuses with blackboards full of equations. And sure, the full mathematical machinery is demanding, but the core ideas, the ones we've been walking through together tonight, they're not beyond anyone. Quantization, the idea that energy comes in packets, wave-particle duality, the idea that things can behave like waves and particles depending on how you look at them. Superposition, the idea that a system can exist in multiple states at once until something interacts with it. Uncertainty, the idea that certain pairs of properties can't both be known precisely at the same time, not because of our limitations, but because of nature's. Entanglement, the idea that particles can be correlated in ways that have no classical explanation, connections that hold across any distance. These are strange ideas, yes, but they're also clear ideas once you slow down enough to let them settle. And what's beautiful, really beautiful, is that these ideas work. They predict the outcomes of experiments with staggering accuracy. The magnetic moment of the electron, calculated using quantum electrodynamics, agrees with experiment to more than 10 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. No theory in the history of science has ever been tested so precisely and passed so completely. Whatever quantum mechanics is telling us about reality, it's telling us something true. We just haven't fully figured out what that something is. So let that sit with you as you drift off. The universe is stranger than it looks. The solid floor beneath you is mostly empty space, held together by quantum forces. The light from your phone was emitted by electrons jumping between energy levels that Max Planck first described in a desperate act of mathematical improvisation in 1900. The atoms in your body were forged in stars that lived and died billions of years ago, and the nuclear reactions that powered those stars are governed by quantum tunneling, particles slipping through barriers they shouldn't be able to cross. You are, in a very literal sense, a quantum mechanical phenomenon. Everything you see, everything you touch, everything you are, is downstream of those strange rules that a handful of physicists stumbled onto a little over a century ago. And the story isn't over. Somewhere right now, someone is working on a quantum computer, trying to coax a few dozen qubits into maintaining their coherence long enough to perform a calculation no classical machine could match. Somewhere else, someone is cooling atoms to a billionth of a degree above absolute zero, watching them merge into a single quantum state, a Bose-Einstein condensate, a blob of matter behaving as one. Somewhere, a theorist is scribbling on a whiteboard, trying to figure out how to make gravity and quantum mechanics speak the same language. And somewhere, a philosopher is sitting quietly with the measurement problem, turning it over and over, wondering whether the answer is something we haven't even thought of yet. The universe is under no obligation to make sense to us, but it has given us just enough clues to know that something extraordinary is going on beneath the surface of things. And the fact that we can lie here, in the dark, and think about wave functions and superposition and entangled photons flying across the void, that we can hold these ideas in our minds, even if we can't quite picture them, that's remarkable. That's worth marveling at, quietly, as the night gets deeper and the thoughts get softer and the edges of everything start to blur just a little. So let them blur. Let the ideas settle where they want to settle. You don't have to hold on to all of it. The universe will still be strange and wonderful in the morning. The wave function will still be doing whatever it does, whether anyone is watching or not. And you, made of atoms, made of quantum fields, made of the same stuff as stars and empty space and everything in between, you can rest now. The story will be here when you come back to it. It's been unfolding for 100 years, and it's nowhere near finished. But for tonight, this is a good place to let it go. Close your eyes, breathe, and let the quietest, strangest, most beautiful theory ever devised carry you gently into sleep.